So this will be a benchmark day. We'll look back on that fondly. So Chuck, what's been bugging you lately?
I'll tell you, I don't know if it's bugging me. Maybe I'm happy about it. Maybe the entire human race has something to be hopeful about. You know how I feel about climate and the climate crisis.
Right.
But so I wake up this morning and it's all about fusion. Fusion everywhere. Everybody's talking about fusion, fusion, fusion. I'm like, whoa, is this a good thing? Or are they yanking my chain? Are they just making me, what are they doing? Are they doing the Lucy pull the football away from me? What are they doing? What is happening? What is happening with the fusion?
Oh, okay. So the highlight is at one of the national laboratories, Lawrence Livermore National Laboratories, where they among all the national labs are, one of their major tasks is as shepherds of our nuclear arsenal. Okay, the nuclear fuel, basically. So
right. Yeah.
radioactive materials that might be used in weapons, and it is funded by the Department of Energy, not the Department of Defense. So that in fact, the total amount of money we spend on defense is not only the DoD's budget, but an important fraction of the Department of Energy's budget that involves weaponry, basically. Okay.
Right. Yeah.
So there they have the world's most powerful laser. And what they do with a bunch of these lasers is they aim them all at a tiny target and they cause the target to explode. All right. That alone is not okay.
Sounds like America so far.
Well, what's new about this? Because we've been blowing shit up for like forever. So if the target is uniformly heated, evenly in all directions, and the material is very uniform in all directions, so there would be a spherical shape, then the explosion creates an implosion on the other side of that explosion, right? You can't just have stuff come out unless the Newton's law for every action is an equal and opposite reaction. So the explosion that comes out creates an explosion that points inward. And that creates very high pressure and very high temperature. And under those conditions, you can take two atoms, light atoms, and merge them into a heavier atom.
Sweet.
That takes a lot of high temperature to accomplish. Because let's take the lightest atom of them all, which is what?
I don't know, maybe hydrogen?
Hydrogen, you got it. So hydrogen in its nucleus has one proton. And helium in its nucleus has two protons. Plus two neutrons. So how am I going to create a helium atom from a hydrogen atom? So you got to get a bunch of hydrogen atoms together. All right.
Together.
Well, here's what no one is telling you in the news, but it's obvious when you think about it. What do two protons want to normally do? They're both positive charge.
They like each other, but they don't like each other because they're alike.
Okay.
It's like when you meet somebody at a cocktail party and they remind you of yourself, and you're just like, I don't like that dude. I don't really like that. I don't want to be over there talking to that dude.
Chuck is still in therapy, people, just so you know.
I know, exactly. It's like, it's a simple question, Chuck. Where did cocktail parties and liking people come in? Yeah, but they want to get away from each other, right?
So these are like charges. So in the case of two protons, they repel each other. So how do you get them to come together as a new helium nucleus if they want to repel? So this is like rolling a ball up a hill. All right. If you don't give it enough energy, it's not going to reach the top. It's not going to reach the top. Okay.
There you go. So
if you roll it faster and faster, giving it more and more energy, eventually the ball will reach the top and tip and go over and fall on the other side of the hill. That is precisely what's going on with two protons. Here it goes. The two protons want to come near each other, but they repel. Let's boost the temperature, which speeds everything up. They get closer to each other before they repel. Boost the temperature some more. They get even closer. There's a magic temperature at which these protons will come close enough so that an entire new force operates. It would have to be a strong force in the nucleus to keep two protons together. In fact, the name of that
quantum love. That's called quantum love.
Oh, where's that disco? So I remember Jungle Love. Remember Jungle Love? We know quantum love.
Jungle love.
Yeah, quantum love is like
quantum
you resist
love.
until you cross over the barrier, and then you're there. So when they cross that barrier, a strong force that operates in the nucleus takes over. It's one of the fundamental forces of nature, and it's called the strong nuclear force. There it is. Okay. That's what it's called. It is a very short range force. It only operates on scales as small as the nucleus itself.
Wow.
But you have to get there for it to grab a hold of you and make a new atom. That's why it takes high density, high pressure, and high temperature to overcome this.
All right. So
that is
I'm with you.
That is thermonuclear fusion. Thermo is hot. Nuclear is the nucleus.
Right.
Fusion, they're bringing it together. It turns out that when you do that, your products have less mass than when you started with.
Whoa.
Oh my gosh. Where did the mass go?
Exactly.
E equals MC squared. My lovely. So the mass on the one side of the equation, if you lose it, it manifests on the other side of the equation as energy.
There you go.
There it is. And so they manage.
That's fusion.
So at the Lawrence Livermore Laboratories using lasers, and by the way, they've led the world in lasers like for decades. In fact, people on the inside call it lasers in lasers. Okay, Lawrence Livermore National Lab. Okay,
lasers, and lasers. That's
in lasers, right. So anyhow, so they have managed to. You can add up how much energy it takes to turn on the lasers and fire them, and then look at how much energy comes out after you've done this. And they got 50% more energy out of this than the energy of the lasers that went into it.
That's amazing.
Amazing. First time that's ever happened.
Now that's an energy source now, because you got more out than you got in, which is what I want to know. Which is, so what did it take? What would it be? What did it measure? Like, is it anything significant? Percentage wise, that's great. But like, what would it take to turn this into an energy? It would have been great if it just
broke even. That would be a major milestone unto itself, right? But the fact that they got 50% more energy out than they put in, it says, oh my gosh, we can get the physics to succeed. And for my money, I'm saying if the physics works, then it's just a matter of time before engineers say, I got this. I'm gonna make something out of that. I got this. And so
that's amazing.
Yeah. And so I'm very much look forward. There's a civilization pivoting on this result. And by the way, what I just described to you, the sun does every moment of its life. The problem over all these years is that, of course, we've known how to make fusion. We've known how to make fusion since 1949 or something. When the first fusion bombs are called hydrogen bombs. They're using hydrogen. That's what I just told you. Two protons is merging hydrogen atoms, nuclei together. So we've known how to make fusion forever. The challenge is not how do you make fusion, how do you control it?
Yeah, because you don't want the electric company having to move to a new city because there's no city left.
Right, exactly. So while in America, we're really good at blowing stuff up, we're less good at controlling that explosion, right? So the Holy Grail was, can we undergo fusion in a controlled way where one day you might be able to throttle it or contain it or transport it? And we'll finally get maybe that ending scene in Back to the Future.
Right.
Here's your cue, Doc.
Marty, it's your kids, Marty.
And do you remember how, and Marty says, but Doc, where are you going to get the energy? There's no lightning bolt and there's no room for, what are you going to do? And remember what he does?
He dumps a bunch of trash into the flux capacitor, which is now powered by fusion.
It's Mr. Home Fusion, right? It was like a blender.
That's right.
He puts it in, and that undergoes nuclear fusion. And so one day, perhaps, we'd have fusion reactors in every car. And then you could
wow,
there it is. So this would transform civilization, even regardless of the carbon footprint that it doesn't have. It would transform civilization, but it also happens to not have a carbon footprint. So we could stave off this growth of fossil fuel burning and greenhouse gases, and we'll still have to recover from the damage we've already done, because a lot of the carbon dioxide got took into the oceans. And if you start removing it from the atmosphere, it begins to come out of the oceans, and it'll do that until it becomes equal again. So you got to recover that. But it is the future. And just I might tip my hat to the physicists and engineers at the national labs. And this whole thing was important enough. It was a press conference announced by the Secretary of Energy. So, we're chomping at the bit.
So then it is good news.
Good news. I suspected accurately. Yes.
All right.
And we've been at it for decades. Just thought I'd tell you that. And so this will be a benchmark day. The first and second week of December in the year 2022. We'll look back on that.
Another day in December that will live not in infamy. What is it when it's a good thing?
Femi.
Just Femi.
Live in Femi. Okay. All right, Chuck, we got to end it there.
All right.
All right. But there's way more about fusion. That's another show. We'll talk about stars. There's more and why stars explode. All right. I'll leave a teaser here. You ready? Fusion, you get energy by combining little atoms. Fission, you get energy by splitting big atoms.
Okay.
But wait a minute. There's got to be some point in the middle where these two phenomena meet. What happens then? Therein are the seeds of the undoing of great massive stars in the universe. That's a whole other explainer we'll get to. Oh, yeah. Nuclear fusion in a nutshell. This has been yet another StarTalk explainer. Great to have you join us, putting fusion back on the map. Chuck, always good to have you.
Always a pleasure.
Neil deGrasse Tyson here. Keep looking up.